Good afternoon, everybody. Oh. Just before we meet our speakers, there's just one or two little things we have to go through. I see a few familiar faces, so apologies if you are hearing this more than once, but we'll just go through a few things. First of all, we're going to hear from the speakers, but we've also got a little bit of time allotted for a Q&A session towards the end, and we really do want to hear your questions. We are going out live onto YouTube, and we're also sending this out to screens throughout the museum. So during the Q&A session, I'm going to come up to you, listen to your question, and then it's slightly awkward, I'm going to repeat it. Now, some people have the idea that the best thing they should do is just shout, and that will solve the problem. No, it's so that I'm putting it into the microphone so that we can get it out to the speakers. So you relax, you don't have to shout or project or anything like that. We will repeat it. If I completely misrepresent your question, you can shout at me. That's fine. But we're going to get on with this in just a second. But as always, I'm going to do a little bit of reading so I get this right. Our speakers today are Caroline and Floor. And Caroline is a polar climate scientist with the BAS, whereas Floor is a cloud physicist. Okay, just correct me if I'm getting this wrong. And together are part of the Atmosphere, Ice and Climate team with the BAS. And so, Caroline, your work is with climate model simulations for future projections. Yep. Okay, I'm doing well with this. Okay, and Floor, you are looking at focusing on improving the representation of. I'm just going to say this phrase because I don't know what it means. Mixed phase clouds over the southern oceans and climate models, or in climate models.
That's right, yeah.
Yeah, okay, excellent. Well, I haven't really covered myself with glory there, but I'm going to hand it over to Caroline and Floor. Take it away, guys.
Thank you for this excellent introduction. And I think as this slide already shows, we're interested in also the larger picture of water in the climate system. So we will definitely focus on sea ice and clouds in this talk. But we'll hope to bring it back into the context of water in the climate system. So you may be all familiar with the water cycle. And in a nutshell, the water cycle has to do with how snow and ice from mountains melts and then via rivers and meltwater goes into the oceans, where it might evaporate into clouds, then condense as it goes higher into the atmosphere, condense into clouds, is transported by clouds, and then eventually it will precipitate in the form of rain or snow back onto the mountains or on the land. And this is really, in a very brief nutshell, the water cycle. What you might not know about the water cycle is that it's also very important for the transport of both water and energy in the atmosphere, and that it has a very important role in our climate system. So we will be talking about specific parts of this water cycle. Please.
Yeah, so sea ice is what I study, and I guess you probably don't normally think of sea ice as part of the water cycle. Now, obviously, sea ice is frozen water, but because it forms from the frozen ocean and then melts back into the frozen ocean, I guess it's not directly part of that cycle. But it's still really important for the ocean circulation and also for climate. So that's what I'm going to talk about in maybe about 5 minutes. You'll maybe have an idea of why sea ice matters in the big picture.
And as we've announced, I'll be talking a little bit more about clouds. And clouds, as I mentioned, are responsible for the transport through the atmosphere of water and energy. Clouds are very interesting to us because it's still a little bit unclear whether they are actually heating or cooling the Earth. And they are therefore one of the largest uncertainties when we look at climate models' predictions of future climate. So I'll be talking about that right after Caroline.
Fabulous. So this is going to be a talk in 2 parts. Part 1 is all about sea ice. So we're going to start with a very minor interactive element. And I just want a little show of hands if any of these images are what you think of when I say sea ice. So does anyone think of, say, a polar bear on some sea ice? Show of hands if that's kind of the first things. Yeah, so those of you watching on live stream, I think that was kind of most of the room. That was a raise of hands. You can raise your hands for another one as well, people in the audience. So the next one is a map like this. So this is the amount of the Arctic Ocean. So we've got America at the bottom. England's just off the screen at the top right. And this is the amount of the Arctic Ocean that was covered by sea ice at the end of summer in 2012. So that kind of image, anyone seen that before? Think of that one? Yeah, so again, I think that's kind of a good proportion of the room. Now, I feel like I can already tell that the next ones I'm not going to have so many hands, because I did wonder if anyone just kind of thinks of something completely different when I see sea ice. So if you think of anything else, kind of quick picture, then just raise your hand. I'm not going to be able to ask you what it is, but anyone else? No, no other quick hands. And I already know that no one's probably going to do this, but some of you might just be like, I have no idea what sea ice is. So anyone really not know? Oh, great, cool. So we can get really stuck in. So sea ice, as I've said, is the frozen ocean. And the ocean at both poles, so the Arctic in the north and the Antarctic in the south, changes a lot each year. So as we go into winter and there's much less sunlight, the atmosphere cools and then the ocean freezes. And then that happens, and the ice can get up to typically a couple of meters thick, but in the Arctic it can be up to kind of 20 meters in some very localized regions. And then it melts back again in summer, and that happens every year. So just to look at some of these maps again to kind of give the big picture, this is an image of the Arctic, but this is now what it looked like this year in September. So when it was the end of summer, and there was just, you can see how much area was covered, and the yellow line shows what we used to expect. So we're already getting an idea here that Arctic sea ice has been changing quite a lot as the climate has been changing. Now, the end of the Arctic summer is the end of the Antarctic winter. And so this is the Antarctic on the right, and about October, it's a little bit later, in 2015. These are images from NASA, and this is an image from 2015. So we can see an almost circular ring of sea ice in the oceans around Antarctica. So then we fast forward about 6 months, and we get this very different picture. Now, on the bottom left, we can see Arctic sea ice now in March this year. So, and we can see that the area has changed massively. Actually, the change in area that's covered from the top to the bottom is about equivalent to the whole landmass of Canada. So this is a really huge seasonal change. If we look at the Antarctic, we can now see that there's very little sea ice left in kind of some of the bays around the coast. And actually this change, so the amount of sea ice that is changes in the ocean each season, is about equivalent to the whole landmass of Antarctica. So essentially we're doubling the surface of the southern hemisphere that is covered by some kind of white frozen surface each year. So these are huge changes in the surface of the planet that happen every year. Now, the next question is, well, why do we care? So there are many reasons to care about sea ice. Some people live on it. Some people have to travel through it to do scientific expeditions or to trade. And lots of animals live on it, like the polar bear, or kind of in and actually even underneath the ice. But I'm a polar climate scientist, and so I'm interested in sea ice in the climate system. This is an image from Bass's photography archives, which shows the edge of the ice. And what you can probably see, first of all, is that the left is blue, dark, and the right is white. It's bright and it's reflective. And that means that it reflects sunlight, the energy from the sun, or shortwave radiation. And that's been happening for a long time. So what then happens if we start to melt the ice through a forcing like climate change? Well, we start to melt the ice and we take away this bright reflective surface. And instead, the ocean is dark blue and absorbs heat. That is then re-emitted back to the atmosphere, and the atmosphere itself warms up. So what that means is, at the pole, we're reinforcing the warming that's already happening from climate change. And that could be really important for our weather systems. So one of the things that normally drives a lot of our weather systems is the fact that the pole is cold and the equator is warm. The Earth wants to transport heat from the equator to the pole, but it's spinning, and we end up with the jet streams, or the winds that flow from west to east. And they control a lot of our weather patterns in the news. Sometimes if we have an extreme event, it rains a lot, it's because the jet stream's doing something strange. So if we start to mess with this pattern because we warm the pole more than the equator, so we reduce this difference between the pole and the equator, we could mess with the jet stream, and therefore we can mess with our weather. Now, this is a really contentious issue as to just how much it's already happened and just how important it will be in the big, complex picture of climate in the future. But it does mean that these changes that are happening, and for us, particularly in the Arctic, because it's where we're closest to, are really important for what would happen in our weather. So that's looking up from the sea ice into the atmosphere, but we can also look down. Now, if you've been to our stand, you'll have had a bit of a spoiler for what I'm about to talk about next. And to understand what I'm going to talk about next, we need to know a concept called density. And density is mass over volume in school speech, or how much a certain amount of something weighs. So kind of how heavy something is. So different types of liquid have different density. They weigh different amounts. So on our stand, we started with an experiment where we put a green ice cube, here it's going to be a blue ice cube, in a glass of water. And on the left, we put it in warm, fresh water. What happens is that the ice cube melts, the cold water that comes from it sinks, and then that mixes. That's indicated by my arrow. So warm water from underneath comes back up and heats the surface and carries on melting the ice cube. So the ice cube goes away quite quickly. However, we have another one which is exactly the same, but I started off with salty water inside the glass. And here, we only end up with a blue layer on top, and the ice cube lasts longer. So what's different? All we've done is added some salt to the water underneath. But what salty water is, that is heavier too. So if you've ever been swimming in the sea, particularly somewhere like the Mediterranean, or if you're very lucky, the Dead Sea, it's so salty that it's much easier to float, because you feel much lighter compared to the salt water. So here, although the cold water is heavy, it's outweighed by the density, the heaviness of the salty water underneath. And that means that it's much harder to mix. The cold water can't sink anymore, it stays at the surface and stays in a cold layer that keeps the ice cube. So in the climate system, a similar thing happens, and each season we have sea ice that forms from salty water. But then we start thinking again about density. So when the ice forms, although the water is salty, actually the ice becomes fresh. So you can't get that salt into the ice. So after a while, the salt comes out. So we're adding salty water to the ocean when ice forms, and that's heavy and dense and wants to mix. It wants to sink, and that's really important for ocean circulation and ocean patterns, because that water wants to sink into the ocean and be carried away. A few months later, when the ice then melts, it's fresh water that wants to sit near the surface and doesn't want to mix. So we're changing the ocean through the sea ice. So we're therefore interested in what's happening in a changing world. And in a warming world, we've already talked a bit. So as the world gets warmer, in the Arctic, as we might expect, ice has been melting. We've seen that already with the maps earlier. And this is a time series back to 1979. Gradually, we've got the wiggles up and down from year to year, but ice has been melting. In the Antarctic, something surprising has been happening. So we've got the wiggles again, and actually a few years ago we had a sudden drop. But you can see the line shows that there hasn't been much change in Antarctic sea ice. So there's a big puzzle there, what's been going on. And one of the reasons is something to do with this freshwater idea. And the idea is that freshwater melting from the ice sheet on top of Antarctica has made the surface of the water fresher. And like I said, that makes it harder to mix, and it helps the surface keep cold, and that could mean that it's easier to form sea ice. So we're going against this kind of big picture warming. Now, how true that's going to be, how far into the future, is one of the big puzzles that I work to understand, and in particular, using climate models, like Ed mentioned at the beginning. But that is a whole other topic, so do ask them at the end. But for now, I'm going to hand over to Floor to tell you about clouds in the system.
Thanks. So I'm going to take you from the sea ice up into the clouds. And first of all, you might wonder, how do clouds actually have any influence on our climate? So they're what we call radiative effects. So just like sea ice, the top of the clouds can reflect the solar radiation coming towards our Earth, and it will reflect it back into space. So when that happens, we will have relatively cooler temperatures at the Earth. But there's also something else that's happening, because clouds can also trap the heat that is emitted by the Earth and send that back to the Earth. You might be familiar with this because we call it the greenhouse effect. We've been talking about it a lot in the context of CO2, but water in clouds can also have that effect. And that will cause a net heating at the surface of the Earth. So we've got these two influences. Then there's a bit more of a complex influence I've already talked about. So when water evaporates from the surface of the Earth, it is transported into the sky, so it lifts. There it can condensate into clouds. the clouds can travel 4 kilometers far away and then precipitate, and when I say precipitate, I mean rain or snow back onto the Earth. So this transport of water and energy is also an important aspect of clouds. So now you understand why whether clouds heat or cool the system is actually very complex. And it's also related to the altitude of clouds, to their geographical location, so where on Earth they are situated, and also to their horizontal and vertical extent. And this is why it's so hard to model this in climate models and to get the exact interactions right, and also to understand how this might change in the future climate. So I've been talking a little bit about why clouds are important for our climate, but what exactly are clouds? So we've been at the stand here for a few days now. I've asked this question to a number of people, and actually many people have been telling me that they think clouds consist or are made out of water vapor. And that's a bit tricky because, yes, there is water vapor in clouds, but we can't actually see vapor. What we see when we look at clouds are actually tiny, tiny droplets, condensated water droplets that are suspended in the atmosphere. And they're suspended there because they're very small and because there's some vertical air motion keeping them there. Now, these droplets, I'm going to ask you to imagine that we have microscopic vision and that we can really, really see at the level of this tiny droplet. At the level of this very tiny droplet in the atmosphere, we'll see molecules going constantly in and out of the droplet. And this in and out, going in and out of the droplet of the molecules, we call that evaporation and condensation. Now, this droplet is very small. We'll only have a few molecules in there. They'll be holding each other together inside the droplet, except that if there's only a very few of them, it will be very easy for a molecule to escape out of the droplet. Now, once they start escaping, there's even fewer of them, and they'll keep escaping. So that's evaporation happening. So what have I been telling you? Actually, my microscopic droplet is evaporating faster than it's condensating. So my cloud has just literally vanished in thin air, hasn't it? Yet clouds exist, so there's something else going on. So there's actually not just these droplets, or there's not just water in clouds. What if, instead of only water, we would also have tiny solid particles? If we have a tiny solid particle that's soluble, so it will actually be attracting water vapor onto it, then the water vapor can condense on my tiny nucleus, and it starts from a larger size. And because it starts from a slightly larger size, it can keep on growing and keep on growing. It will actually grow, in order for a tiny droplet, a cloud droplet, to grow into a rain droplet, for example, it will have to grow 1 million times. And that's quite a lot. So next time you'll be walking through the rain, you might appreciate a little bit more all of this work that this tiny particle has been doing to fall onto your head. So these tiny, tiny solid particles I've been talking to you about, we call them aerosol, or cloud condensation nuclei. And aerosol come from aerosolution. You might have heard about it already because we've been talking about it a lot lately. And they're just a suspension of tiny solid or liquid particles in a gas. Now, where might these aerosols actually come from? Well, we're not responsible for everything as human beings, so there is also natural aerosol in the atmosphere. This image gives you a modeled image, actually, of different types of aerosol. The brown in the middle of the image represents dust and sand coming from the deserts. We have some green in the image, which is organic and black carbon, so that might be forest fires. Other and natural types of aerosol can include pollen, sea salt. You have quite a lot of that. Whereas human-made aerosol can come from combustion of fossil fuels or biomass burning. So as you will also see in this image, Antarctica, which is at the bottom, you can see that we have a lot of natural aerosol there. And that's why it's such an interesting region to study aerosol and cloud formation, because it has very little influence from the particles that we emit as human beings. So we can have a look at how that used to be before we started emitting these particles into the atmosphere. So now how do we measure clouds and aerosol? Well, we can either send a signal from the ground into the air, into the clouds, And that signal will be reflected back, and it will give us an indication of how high and thick the clouds are. As I mentioned, clouds reflect sunlight, so we can use satellite to see what that signal is that's being reflected back to us, and we can have an idea of the extent of clouds and their duration. But we can also go to Antarctica, and we have special instruments that make images of cloud particles and of ice particles in clouds. And we can put those instruments on an aircraft and then fly through the clouds and have a better idea of what clouds really consist of. And then we have other instruments which will suck air through it, and we can have that air sucked through a filter, and we take those filters back into our lab, and then we'll use those filters to analyze them, and we'll search for a very specific type of particle, which is called an ice nucleating particle. And I suggest that if you want to know more about ice nucleating particles, you come to our stand, where we also have a number of very exciting experiments to explain to you a little bit more how and what our science is about.
Cool, and I'll just say that our stand isn't in the ticketed area, so do come in, it's downstairs. So I'm going to finish now just by coming full circle onto the water cycle. So we talked a lot about this, and we said that after water is in the clouds, it then comes back and essentially falls of rain. Now, in the UK, we're used to our winds coming from the west, bringing moisture in, and maybe rising up over the Pennines, perhaps, and then dumping rain on us. And actually, a similar thing happens in Antarctica. So this picture on the right shows Antarctica, and where there's the red is where there is wind flowing from west to east. And you see the peninsula sticking out of Antarctica towards South America at about 10 o'clock, and that is a very high area. So exactly the same thing happens. Winds bring moisture over the peninsula and dump snow, which eventually then adds to the ice sheets and eventually, much, much later, flows into the ocean. And so the water cycle becomes complete. So this is just some of what we do, and a picture to finish. Thank you very much to listen to us both, and we would love to answer loads of questions.
Well, thank you very much, both. That was a great talk. Folks, we just have a few minutes. I have to be very strict with time with this one, but we've got a few minutes if anybody has any questions that they want to ask. If you raise your hand, and I will, as I say, a bit awkward, but I will come in and repeat things. Well, can I start off with one?
Yeah.
We talked about ice and we talked about clouds, and you did mention things like rain. Is there a sort of continuous model, sort of from the top down, or do you treat these things sort of separately? You know, are your models, if you like, complete? Can they take everything into account, or are we not there yet?
Yes, so our climate models, essentially, they have most of these processes in, but they're divided into kind of blocks. So actually, typically, our climate models, they have an atmosphere component and an ocean component, and a sea ice component in between. And so we model kind of from throughout the atmosphere in one block, and then we have some way of making the ocean and the sea ice communicate then to the atmosphere. So the kind of the modelling is done a bit separately, but in your model, kind of every 10 minutes that you imagine time has gone forward in your model or so, they will communicate with each other. So our climate models that we use to predict climate change are the full picture.
So I would like to add to that in terms of clouds, because we also have that in models. The problem with clouds, and you've seen that during my talk, the scales are so different. So clouds, you can have them on very large scales, but I've been talking to you about the microscopic scale. And so in climate models, it's really hard to get those really small scale features in, because you would have to use a lot of computing power to get that resolved in the model. And therefore, in climate models, the representation of clouds can be still quite coarse. And they rely on more precise, smaller models that feed into those really big models, the information that is aggregated, actually, from the really small scales. Aggregated is something like you would average it, I guess, in a certain sense.
Well, thank you very much. So, with my background as an astronomer, these problems are very familiar. I was kind of hoping that actually you might have cracked it, and then maybe we could just sort of steal your techniques. Yep, if you bear with me.
Hi, I'm very interested in seeing that first slide again with all the wonderful cloud formations. Because I want to ask, do we have the same sorts of cloud formations in Antarctica as we we do in the northern hemisphere.
Okay, so the question was, do we have the same kind of cloud formations in Antarctica as we do in the northern polar regions?
That's the same picture, I think, the ones you're talking about. So I would say that the formations of clouds kind of depend also on the orography that's beneath it. So this cloud formation, you see a little bit of layering. It's a bit behind the text with the layering in the clouds. And that has to do with the wind patterns. So you will see different cloud formations, and those are more related to the shape, I guess, of the Earth underneath. If there's mountains or any kind of that will cause undulations in the wind patterns that will actually go further higher up into the atmosphere, and that will cause turbulence in the atmosphere, which will cause the air to rise and fall, and that will cause these different shapes. What's different in Antarctic clouds from in the higher latitudes is that, well, it's colder, so they are colder, and we'll have these mixed phase clouds. So I've been talking about water droplets, but you can also have ice crystals. And actually, water droplets and ice crystals can coexist in a cloud. These water droplets, they are at super cooled temperatures. So these are water droplets, and I will show you that at our stand if you like. We can have liquid water at -5 to -38 degrees, actually. So this liquid water will be present in the cloud. And these mixed phase clouds of water and ice, we have them quite a lot in Antarctica. We have them also in more temperate zones, but not quite as often. So that's a big difference.
And do the high winds influence the cloud formations as well? High winds you have on.
So the question is if high winds influence the cloud formation as well. Actually, I don't really have an answer to that question. So my guess is it would influence the clouds to the extent that, and I haven't been able to address that in my talk, so thank you for the question, is that the high winds, they blow over the sea ice and they bring snow particles and tiny snow crystals into the atmosphere, really high into the atmosphere. And these ice crystals serve as ice nucleating particles. And that will allow these ice crystals to grow in the clouds in the first place. So yes, the high winds actually also bring a lot of nuclei into the clouds.
I think we've got time for one more question. We'll go to this young man here.
Okay, well, hello again. I just wanted to ask, you said you're not sure whether the clouds act more as like a trap for heat or does it cool the rays of the sun? But how do you measure those things?
Wow, that's an excellent question.
It's a great question.
And I knew I should be scared because I've seen you at the stand. I know you have very, very good questions. So the question was whether, I was saying that we weren't really sure whether clouds had a net cooling or a net warming effect, and how do we measure that? Well, there's something which we call the radiative balance. So we use models and calculations. We can measure the amount of sunlight coming to the Earth, and we can measure the amount of infrared radiation that's being reflected back by the clouds. And with this information, we can feed that into models, and we get an idea of how much it warms up. What the difference between the two effects is.
Folks, I know we would ask questions all day, but I'm afraid I've got to keep us quite strictly to time. So first of all, can we thank our speakers again, Flora and Caroline. And as they mentioned, they are staffing the stands, and that is not in the ticketed part. It's in the learning spaces, and so please do go and visit. As they've got cool stuff to look at and to play around with, and of course you can ask them other questions. I've got a slightly odd duty. I'm going to remind people there is still the Penguin Parade, and that will be happening at 4 if you want to dress as a penguin, or I guess just follow the other people dressed as a penguin, to go down onto the Thames, and actually the captain is going to honk the horn. I keep saying honk the horn. That is not the proper term, I'm sure, but yeah, please take part in that, and we have one more talk for this series of sessions. So thank you very much, everybody. Thank you to our speakers once again, and hope to see you again. Thank you.